Hello everyone. So today we are going to do Norton's theorem. So in the previous classes of this particular module, that is the DC network theorem, so what we have done already, we have done already superposition theorem, the Thevenin theorem. Now today we are going to do the Norton's theorem. So already we have discussed some new theorem except this KVL, KCLs, those theorems already, because those are the school level physics. Already we have done in the school level. Here also we have done in the primary classes. So here in the Norton's theorem, so as we have done in the superposition theorem and Thevenin's theorem, here also the same thing, same procedure we will maintain to understand the theorem, so that you will be very easily understand what is a theorem. So in the previous theorem, what we have done that how we can solve the theorem, what is the statement of the theorem, what is the conditions to apply this theorem, what are the steps to solve the theorem, and if there is any limitations of the theorem. Superposition theorem, there we have seen this some conditions to apply the theorem, and after that in each case we will see that the same conditions are applied for Thevenin's, for Norton's, for maximum power transfer theorem, whatever is the theorem. So the basic point is that Norton's theorem is basically an application of Thevenin's theorem. So just in a small manner, if we recapitulate the what is Thevenin's theorem. So in Thevenin's theorem we have done that there is a circuit. Say, okay, coming to this circuit, okay, it will be better to understand. See, this is your circuit. So you have to solve, you have to find out that through RL we have to find out the current. Okay, so if we apply Thevenin's theorem over here, so what we have done over there, so as per the Thevenin's theorem, first remove the RL, load resistance we have to remove, make that terminal open, and find out what is the open terminal voltage, and whatever is the voltage appearing at the open terminal, that will be our VTH, that is the Thevenin's voltage, that will act as the equivalent voltage of the circuit, or the new circuit that we are going to make in the last. Step 2, what we have done in Thevenin's, so we have removed whatever source is source is present in the circuit, voltage, maybe current, and we have made that circuit independent of source, and we have viewed from the open terminal, and we have find it out what is the equivalent resistance of this circuit. So that is our RTH, okay, Thevenin's resistance. And in the last, what we have done, so in the initially we have find it out equivalent voltage, that is now our voltage source. After that we have find out the equivalent resistance, that is our the now series resistance, and at the fast we have disconnected the load resistance from the circuit, and that will be connected in series. Now we have to find out the simple series current, that will give us the load current. So that was our Thevenin's in short. And now I am telling that this Norton's theorem is an application of this Thevenin's theorem. So first point you remember, if we very good understand the Thevenin's theorem, then we can very easily understand this Norton's theorem, because the procedures and the concepts are almost same in both cases. So if we come to the use, first use, how to come to the use, then we'll go to the statement. Okay, so it will better understand for you. So I have written over there, it is an application of Thevenin's theorem. So yes, it is an application of Thevenin's theorem. Number two, it is a current equivalent theorem. So if we can remember the previous one, that is the Thevenin's theorem. So there we have studied that in use, that it is a application of voltage equivalent theorem. So Thevenin's theorem was a voltage equivalent theorem, but here I are telling that this Norton's theorem, the current equivalent theorem. So when we are discussing about the current voltage equivalent theorem, that means the Thevenin's theorem, there initially we have disconnected the load resistance, we have removed the resistance on the circuit, we have made the terminal open, and we have find out the open terminal voltage. But here it is told that it is a current equivalent theorem. That means we have to find out some current. Now the point is how we can find out the current. The, we can find out the current by removing the load resistance from the circuit, make that terminal short and find out the short circuit current. So whatever is the short circuit current, that will give us the Norton's current. Okay, so at the end that will act as a current source. See, just try to similarize between Thevenin's and Norton's. In Thevenin's, we have removed RL. In Norton's, we have removed RL. In Thevenin's, we have made the terminal open. In Norton's, we have made the terminal short. In Thevenin's, as the terminal is open, so definitely we will get some voltage over there. No current is flowing, so we have find it out from voltage. In Norton's, as the terminal is shorted, so we definitely we will get some current, and that current is our Norton's current. So like this way there is a difference. Both case we will remove RL. In Thevenin's we will make the terminal open. In Norton's we will make the terminal short. Here as the terminal is open we will get some voltage. As here in the Norton's, as the terminal is short, there we will get some current. So this is the change between Thevenin's and Norton's. Okay, so coming over here, so first come to the statement of this Norton's theorem. Just I think I have given a small overview what is a Norton's theorem. So first coming to the statement, so it is told that a linear active network containing of independent or dependent voltage source, though remember in your syllabus no dependent source is there, correct? So for now just don't think about the dependent source. You have in your syllabus you have only independent source. Okay, and current sources and the various current elements can be substituted by an equivalent circuit containing of a current source in parallel with a resistor. The current source being the short circuited current across the load terminal and the resistance being the internal resistance of the source network. So here what is the use? So as I have told that it is an application of Thevenin's theorem. So whatever is the application of Thevenin's theorem, that must be the application of Norton's theorem. So what was the application of Thevenin's theorem? Thevenin's theorem application was it can be used for where? To simplify a complex circuit to simpler one, to find out current or voltage through a particular branch of a complex network, correct? So Norton's theorem can also be applied to do the same thing. That means to simplify a complex circuit, to find out a current voltage through a particular branch of a complex one. Okay, so now we are going to solve. Okay, use is done. Okay, terms to know, that is very very important, because I always say that I always say to my students that this terms where we can apply this theorem and the concept, if we understand, so it will be very easy for you to apply the concept, where we can use the theorem, where we cannot use the theorem, why we cannot use the theorem, why we can use the theorem. So those concepts, so your base should be strong, or you always say. So for that I always say that, so say, as you have already seen that in each theorem I am intentionally placing those terms to know. So the linear, bilateral, active, passive. So I have seen that students always forget what is linear, what is non-linear, what is bilateral, what is unilateral, what is passive, what is active. So those terms are very confusing. So if I do same thing repeatedly, day by day, same thing if we do, it will be remembered to you. That's why I have given to you. The first point is linear. So what is linear? I have told. So a linear element is such element through which the VI characteristics is linear. Now what is VI characteristics is linear? That means the VI characteristics will follow the straight line equation. So what is straight line equation? Y is equal to mx plus c. So now in a graph, if we want to plot a straight line, so what we have to do in x-axis, we have to take some we have to take the v, and when y-axis you have to enter the current. Okay, so now if the voltage value is increasing and if the current value with that current value increasing, so what we'll get? We'll get a straight line. So that is actually the linear property of an element. That means when voltage is increasing, current is increasing. When voltage is decreasing, current is decreasing. That is the linear property. Okay, and an element which has this property is a linear element, and a circuit which contains linear element is a linear circuit. And we know that Norton's and the theorem can be applied to the linear circuits only. Okay, coming to the number 2 point. What is the number 2 point? The number 2 point itself, it is bilateral. So bi means both. Already repeatedly we have seen that. So bi means both. So for both direction through an element through which both direction current can flow, that is a bilateral element. So for your understanding, so say here in this particular diagram, I have seen a real pictorial view of a resistor, and in the right hand side we have taken a symbolic representation of a resistor. So in the symbolic representation of a resistor, if we connect a source, so if we connect a source left hand side, so current will flow from left to right. If we connect a right hand side source, the current will flow from um, right to left, provided the connecting side should be high at higher potential, correct? Otherwise it will flow in the opposite direction, na? So we have to remember that one. So that is the point is, so if we connect this the source over in the left hand side or right hand side, the current will flow maybe from left to right or right to left. So an element through which both the direction current can flow, and due to that, if the property of that element is not changing, then it is a bilateral element. And a circuit which contains bilateral element is a bilateral circuit, correct? And this Norton's theorem can be applied over there. Okay. Okay, now the passive component means which doesn't has its own source of EMF current. Resistor, inductor, capacitor, all are passive components as they doesn't have any own source of EMF, correct? And this Norton's theorem can be applied where it doesn't have any own source of EMF. Now explanation, coming to the Norton's theorem. So Norton's theorem, for understanding the Norton's theorem, as in the Thevenin's I have taken a simple circuit, here also I have taken a simple circuit. So just now check follow the where how the theorem is different from the Thevenin's one. See where I have marked. So this is our load resistance, correct? So this is the voltage source, this is R1, there is R2, there is R3, and there is a RL. And we are assuming that through RL, IL is flowing, correct? Now we have to solve this circuit using the Norton's theorem. So first thing, what is told in the Norton's theorem? It is told in the Norton's theorem that remove RL. After removing RL, make that terminal short and find out what is the short circuit current. So that is the steps to do in the first step of Norton's theorem. So see, coming to the next step, see here there is a RL. So we have removed that RL, we have made that terminal short, and we have to find out what is the current flowing through this short circuit path, that is known as the ISC. S for short, C for circuit. So I suffix SC, that is short circuit current. Okay, so we have our aim is to find out the short circuit current. So as we can see, the source current is producing from the source, it is coming to the node, then both direction it has resistance, and both direction it has a complete path, so current will divide. And we have to find out the current passing through this R2, because whatever current is passing through this R2 is passing through this short circuit part. So if we can find out the current passing through R2, that will give us the current passing through the short circuit path, correct? So to find out that, what we have to do, so first of all we have to find out what is the current producing from those, from source, and that current coming to this node. Then we have to apply the current division rule, as we have studied in the superposition theorem what is current division rule. So after doing that, so first we have to find out the source current passing through R1. Then we have to apply the current division rule to find out how much current is flowing this R2, and that will give us the short circuit current, and it is also known as IN, that is a Norton's current. Okay, so how we can find out this one, the source current? So first of all we have to find out the equivalent resistance. So what we can see over here, so current is coming, then it is dividing between R2 and R3. So we can say that this R2 and R3 in parallel, with that is R1 in series. So see, that is done. So R1 in series with this R2 and R3 parallel. Okay, so we are making this combination of these three resistance to a equivalent single bund. So V by that equivalent resistance will give us a current, main current, source current. So that thing is done over here. This is the Vs by the total resistance of the circuit will give us the main current. So this current, whatever given, they have given a name I. So this I current will come to this node, and then it is dividing. We want to find out the current passing through this branch, and as we know, if we apply the current division rule, so what is the rule? Total current into opposite branch resistance by total summation of all parallel resistance. So total current is this I coming to this node into opposite. We want to find out the current passing through this R2. So opposite of this R2 is this R3. So we will write down like this. Okay, see, just see, ISC is equal to I, the total incoming current, into opposite branch resistance. We want to find out the current passing through R2, so that's why we have taken here R3 by summation of this two parallel resistance. So here this coming current is dividing between this R2, R3. So these are two in parallel. So we have to consider these two. So like this way we have find it out. So this is our short circuit current, also known as the Norton's current. So this is our Norton's current. So first step is done. So coming to the step 2. So in the step 2 it is told that basically, if you have listened to my previous class of Thevenin's, there I have discussed about how to find out the RT, the Thevenin's resistance. So whatever procedure is there, the same procedure will be maintained over here. There is no difference in between this step. That means to find out the equivalent resistance. So what we have to do, again I am telling you. So first step, we have a circuit like this. We have removed the load resistance, we have made the terminal short, and we have to find out the short circuit current. Now this, after that, what we have to do, what is to find out we have to find out the total equivalent resistance of the circuit viewing from this open terminal. And to find out that, we have to remove whatever sources are present in the circuit. In this particular diagram we have a voltage source, so we have to remove the voltage source. And as we know, if we remove the voltage source, we have to make that terminal short. So now check what we have done. See, there is a voltage source, we have removed that one, we have made the terminal short. Okay, and the terminal from where load resistance is disconnected, we have to view from that terminal, and after viewing, find out the what is the equivalent resistance of the circuit. So if we think that some current is flowing through this one, if we just view, just think, just visualize. Okay, viewing means not that we have to go over there, we have to check. Viewing means just view. That means if if current is flowing through that terminal, then how it will flow like this. See, so current is coming to this one, it is dividing. So we can say that these two are in parallel, and with that this R2 in series. Now you can ask me that, so current, if the current enters from where, just check yourself. you will find out the same result will appear. See, current is flowing, coming to the circuit through this node. After coming to this node, it will find out two-way, so it will divide. Some current will flow, some current will flow. So this current will flow like this, it will come over here. This current will flow like this current over here, it will add, and it will pass through this R2. So the same result will appear if we think current is entering from here, or we think current is entering from here. So in both cases we can see that this R1 and R3 in parallel with this R2 in series, correct? See, that same thing is done over here. So R2 in series with this is the R2 in series with this R1 R3 parallel, multiplication by summation. So that is giving us the equivalent resistance of Norton's theorem, that is also known as Rn, Norton's resistance. But remember, a very important objective question is always asked that mm Rn is equal to Rth. Yes, Rn is equal to Rth. That means I have told that the second step, that means to finding out the equivalent resistance of the circuit without any kind of source of the circuit, the same method we are following, removing all the source. We have to view from the open terminal. From here we have disconnected the load, and that's why if the same circuit is taken for the both theorem, we can find out the same result for Thevenin's and Norton's. Okay, so that's why we can say that in Thevenin's we can find out RTH, whatever name we actually we given, and in Norton's we find out RN. So both case the result are same, that's why RTH is equal to RN. Okay, remember this one for the objective question. Okay, now coming to the last step. So last step, what we do in the last step, we are going to connect all the components in parallel. So first we have a, see, first we have a current ISC, so that will act as a current source. There is a current symbol. So with that we have a equivalent resistance, that is Rn, this one. And initially we have from the circuit what we have disconnected, we have disconnected the load resistance. So we have to we have to connect all these three components. That means the first step we have find it out the equivalent current of the circuit, that will be act as a current source. The step 2, we have find it out the equivalent resistance of the circuit independent of any kind of source, viewing from the open terminal, the load terminal. So that will be act as a parallel resistance to that current source. And initially we have disconnected the load resistance from the circuit, that also connected in parallel with the equivalent resistance. So all component, three parallel paths will be there. One will be current source, second is equivalent resistance, that is Rn. So first there is In, next there is a Rn, and last there is RL. Okay, so now if I say you, if I ask you to find out what is the current flow to this RL, so what we are going to do, we are just going to apply the current division rule. See, this one. So this one is the current division rule. IL is equal to the total incoming current. So as we can see that, see, there is a current source, and after that there are two resistors. So from the current source current is coming, then after that node it is dividing between two resistors. What are the resistors? One is the equivalent resistance, second one is the load resistance. So if it is dividing between two resistors, so we directly can apply the current division rule. So that actually we are applying. So what is that? IL is equal to short circuit current, the main current, into, we want to find out the current passing through this RL. So opposite of this RL, parallel is one, this RN. So INT by RNT plus RL. So that will give us the load current passing through the load resistance solved by Norton's theorem. Okay, so it is given what is the name of those one. INT is the internal resistance, IRL is the load resistance, I is the short circuit current, I is the load current, like this. And as we have for the points to remember in the Thevenin's theorem, here also I have given the same steps to remember how we can solve the Norton's theorem. So just do that. So just recapitulating the whole thing that we have done today in a very small manner. So first, remove the load resistance, make the terminal short, then find out the short circuit current that will give that will be used as the current source in the end. Next, what you have to do is remove whatever sources are there, maybe voltage, maybe current, then view from the load terminal from where we have disconnected the load and find out the load resistance, and at the end this initially find it out the current. In the next step, the equivalent resistance and initially disconnected load resistance, all you have to connect in parallel, and using the current division rule find out the current passing through the load resistance. Okay, so this is all about the Norton's theorem. Thank you.